So I'm happy to present our second speaker of today, Alexander Caviedes Castro, who will be speaking on the Mukai conjecture and the Kostant game.
Okay, thanks for the presentation. I would like first to thank to the organizers for this very nice invitation. This is joint work with Milena Pavignac and Silvia Sabatini. So let me start talking about the Mukai's conjecture. So this is a conjecture that comes from algebraic geometry. It is a conjecture that is about Fano varieties and topological restrictions of these varieties. And it's also part of this very important program in algebraic geometry that aims to classify these varieties. So in order to be able to formulate the conjecture, we need to define what the index of an almost complex manifold is. So the index, we are going to define it as the largest positive integer that divides the Ferchen class of the tangent bundle. So the conjecture says the following. We have like a Fano variety of complex dimension n with index rho m and Caviedes number v2. Then we have this inequality. v2 times rho n minus 1 is less or equal to n, with equality if and only if m is a projective space. So in particular, when the index is different from 1, you get these upper bounds for the Caviedes numbers. So you can say a few things about the conjecture. I mean, if this is like a conjecture in complex geometry or algebraic geometry, but you can also ask similar questions in the symplectic category. You can ask, for instance, what would be the analogous of the conjecture? The analogous of Fano varieties in the symplectic geometry category, these are the compact symplectic positive monotone. So you can also change this hypothesis or in the conjecture there. There are also different notions of index. So there is like the index that I just defined, but there is also the notion of pseudo index. So there are like several variations of the conjecture, and there is like also a symplectic analogous. There is some evidence of this conjecture. So we know that the Caviedes number has to be bounded because for every n, there are just finitely many topological types of Fano varieties. We also have this inequality. I think that this was shown yesterday by Professor Godinho. The index is less or equal to n plus 1 with equality if the space is isomorphic to a projective space. And this conjecture has been verified for several classes of Fano varieties, including toric, horospherical Fano varieties. And when I was doing the research for this presentation, I also found like a recent paper by Reinecke that shows the conjecture for Fano Kuiper moduli spaces. So this is something that I have not read, but I just found this last week. So today, what I would like to do is like to show an idea of how to prove this conjecture, and then how to apply this idea for several classes of Fano varieties. I'm going to focus just in one case, that are the coadjoint orbits. But keep in mind that maybe you can use this idea for all other classes of varieties. So the inspiration of the idea comes from the following result of Professor Sabatini. There is like a Kobayashi-Oki inequality, but for different types of spaces, no Fano. These are in the symplectic category. So we have that if you have like a Hamiltonian S1 space with a finite knob empty set of fixed points, then you get that the index of these manifolds are between 1 and n plus 1. So this was proven by Professor Sabatini in 2017. So the idea of the proof is very simple. It's like to find a polynomial of degree less or equal to, less or equal to n, n half of the dimension of the symplectic manifold, and to show that this polynomial vanishes on the integer points -1 until minus rho n plus 1. So because the number of zeros has to be less or equal than the degree of the polynomial, so you prove the Kobayashi-Oki type inequality in this category. So what is this polynomial h? This polynomial h corresponds, is defined as follow. For integers, is defined as the index of the line bundles whose Ferenczi class is equal to m times the Ferenczi class over the rho m. So this is the polynomial that she defines, and then she shows that this polynomial vanishes on these integer points. This polynomial has a combinatorial interpretation in the case of toric Fano varieties. In the case of toric Fano varieties, this polynomial that appears here corresponds to the Erhard polynomial of a smooth reflexive polytope, right? So this is Erhard theory, and also this is consequence. Okay, so the index also has a combinatorial interpretation for those polytopes. The index is like how much you can delay the polytope, so it still remains like integral polytope. And this vanishes at these points because it's consequence, because it's not gonna have interior points. Okay, so somehow what is happening is that Sylvia gets a lot of information. I don't know. She gets information, but somehow you have here the second cohomology group, and you have some line on this second cohomology group, and then she shows you have here minus C1, the Ferenczi class, and then she shows that it vanishes on some integer points of this line. So, and she's getting like this inequality just by looking information on this set. So perhaps, so maybe there is hope that instead of considering one variable polynomial, you can consider like a multivariable polynomial defined on the whole second cohomology group. So maybe you can obtain more information, and also you may obtain this second Betti number appearing in the inequality. So remember, this is the Mukai conjecture, so somehow the second Betti number should be involved. Question?
Yeah. So where are you using the fact that you have a Hamilton resonance?
That is in the proof is relevant because she computes the index by using like localization formulas. So she's able to compute like very explicitly, and then okay, we have like the index in terms of this like sum of rational functions, and then she plays with weights, and then she is able to prove the conjecture, well, this inequality for this case. So what I was saying is that maybe instead of considering like one variable polynomial, one can consider like a multivariable polynomial defined on the whole second cohomology group. So you can actually define like an index map, you know? You can define the following polynomial. So the polynomial that maps a second cohomology class to the index of the line bundle whose Ferenczi class is equal to alpha. So maybe as following the same idea that Sylvia was using, maybe you can try to find zeros or linear factors of this Hilbert polynomial in a similar fashion, and maybe you can obtain some sort of inequalities for the index. So usually when we explain this idea to the people, we also need to explain like a result that is analogous to the algebraic result that we have, like the number of integers, zeros of a polynomial is less or equal to the degree. we also need like a similar algebraic result. So we have the following. No, I mean, if you want to deal with the Mukai conjecture, you will have to have this assumption, right? But you can always have this polynomial, right? So this, you always have this polynomial. So, but of course you want to focus on the meaningful cases. So we have the following algebraic result that is like similar to the one that we had for the lattice points of the line. You have like a polynomial that vanishes on a pointed box with corner n1, ml. Then the sum of n1 until ml is less or equal to the degree of the polynomial. So by a pointed box, I mean like a box with integer vertices that is contained in the first octant, and the polynomial is going to vanishes on the integral points of that box except this corner. So when that happens, then you can conclude that the sum of the entries is less or equal to the degree of the polynomial. Somehow we also need this sort of result to be able to get inequalities. So the strategy is like, okay, so you have like the second cohomology group. So you have somewhere the minus the first chain class, and the idea would be like to find zeros of the Hilbert polynomial around this corner. So that is the idea. So of course, once that you have like a really nice idea in mathematics, the first thing that you want to do is to check the idea. So we wanted to check the idea for classes of varieties that we were able to compute the index. And you have like several classes of these, like for instance, toric varieties, quadrant orbits, and some GKM spaces. So in this talk, I'm just going to focus in one particular case and try to explain this case in full detail. That is going to be for quadrant orbits. So just for quadrant orbits, maybe later we can talk a little bit more about the other cases. So let me establish some Lie group convention. It's the standard one that we use everywhere. So G is going to be a complete group. R is going to be the set of roots. Rho is going to be the sum of the positive roots over 2. S is going to be the set of simple roots. B is going to be a Borel. P is going to be some parabolic of the complexification. As SP and RP is going to be the corresponding set of simple roots and roots associated to P. We are going to denote the set of fundamental weights by lambdas betas. For like a weight, you can always have like a line bundle associated to it. And we have like an isomorphism between the lattice spanned by these weights with betas in this complement to the second cohomology group. So the idea is that we want to really, for the case of homogeneous spaces G mod B, to compute very explicitly the Hilbert polynomial, right? So this map is going to be useful to write like the polynomial in terms of these linear combinations. So the Hilbert polynomial can be computed by using several results. So if you have like a weight and you express it like this linear combination of fundamental weights, then the index of the line bundle associated to lambda, because of the Hirzebro-Riemann-Roch theorems and some vanishing results, it has to be equal to the complex dimension of the holomorphic sections of the line bundle L lambda if lambda is dominant. This corresponds to the irreducible representations of highest weight lambda. So for irreducible representations, we have like this Wiles dimensional formula that gives exactly what this dimension is equal. So at the end, we have very explicitly this polynomial. So this polynomial can be considered like a polynomial in as many variables in this complement. So these are good news because the polynomial is very explicit, and also to show that something is zero in this polynomial is not going to be that difficult. So remember that the idea was to find like a box of zeros around minus C1. So somehow we have like these bases for the second cohomology group. And somehow, okay, we write the Ferenczi class as a positive linear combination of these bases. So the coefficients, we call them m beta. And our hope was like maybe we were able to find like a box of zeros for the Hilbert polynomial. And the size of the edges of these boxes would be, let's say, the m betas minus 1. You know? So if we manage to show that the size of these boxes were the m betas minus 1, then the algebraic result will imply the Mukai conjecture in this situation, because the index of the manifold would be the greater common divisor of these m betas. So somehow our hope was like we could find for every beta as many linear factors as m beta minus 1. So we showed the following. We show that for this Hilbert polynomial, k beta plus j is a linear factor for every beta in this complement, and for all the j's between 1 and m beta minus 1. So this is going to imply the Mukai conjecture for coadjoint orbits, right? I mean, you can just count the linear factors also, and then you this would be like the inequality that we obtain. The sum is less or equal to the size of the positive roots minus the size of the positive roots associated to P. And then you get the Mukai conjecture, because again, this is the greater common divisor of the m betas. Later, when we proved this theorem, we found that this was already proven by Pasquier in 2013. So his proof is a little bit different to the one that we are showing here, because Pasquier's proof is more like a case-by-case verification, and our proof is like more combinatorial. So let me explain now how to prove this result. We have the following remark. If you have like a coroot, and you can write a coroot like a beta tilde plus some gamma, where beta is in this complement, and gamma is a non-negative linear combination of these coroots that depends on P, then this product that appears in the linear factorization of the Hilbert polynomial is equal to k beta plus 1 plus the height of gamma. So if you notice, in order to prove this result, this one, that to show that these are linear factors of the polynomial, somehow we need to find sequences of roots, you know? So we have the following definition. A string of coroots for P and beta is a string of positive coroots that has like this form, and also they have increasing height. We say that the string is good if there are no gaps between the heights, and we say that the string is maximal if the highest height of any coroot in the sequence is equal to m beta minus 1. So if we manage to find these sequences of coroots for P and beta, somehow we are able to find these linear factors for the Hilbert polynomial, and they will imply the Mukai conjecture in this case. So the problem reduces now to find these sort of sequences. Questions so far? Okay. So of course, here we need to ask like a very natural question. So the question is the following. So how do you find sequence of positive roots, right? So of course, when you are taking like a class in Lie group theory, so you have usually the list of the positive roots on the appendix of the books, right? I don't know why you're laughing. So, but so we were, okay, we have the list, we were trying to verify this case by case, and somehow after some point we didn't like this approach. So Milena was looking for like a very, very algorithmical way to find these sequences or roots. So she wanted to find like some sort of algorithm to somehow to make computations in like a recursive way, but without relying on this list. So we were looking on Google, and we found this discussion on Math Overflow. Yeah, I mean, it's like a very natural question, but for some reason we didn't know the answer. So how can we find combinations of how can you write how can you get the positive roots in terms of the simple roots? And we found the answer here by Professor Knudsen. So he says that, okay, you can get like an algorithm if you play like a game. The game is called the highest root game. We also found this game with another name, the Kostant game. So, and I don't know if Professor can tell a little bit the story about the game, because we really didn't find too much information about the game. I mean, it's like in the literature, maybe it appears with other names, but it's kind of obscure. It's like we couldn't find too many references. We found like a notes by Professor Postnikov, and he has studied the combinatorics of this game, but not too much about where it came from.
Taking Kostant, I try to tell everyone, so I'm doing that too.
Well, I wanted to popularize the game also. So this is a game that you play on graphs. You can play this game on any graph. And the idea, this is like a solitario game. The idea of the game is that you place tokens on every vertex. So you can have any graph. I don't know, something like this. And then you place a number of tokens on each vertex. So this placement of tokens is what you call a configuration, and the total number of tokens is what you call the height of the configuration. So you must think the tokens as having coins, money. So you are going to say that a vertex is happy. Okay, you can play this game on any graph, but later I would like to play this game on linking diagrams, of course. But for any graph, you say that a vertex is happy if the total number of coins that the neighbors have over 2 is less or equal to the number of tokens that the vertex has. And otherwise, it's unhappy. In our situation, because we are looking like for sequences or coroots, we are going to play the game on linking diagrams. And we are going to assume that the linking diagrams are simply laced. There is like a variation of the game when the graph is not simply laced, but we are going to assume just for simplicity that is the case. the game, it has some rules, right? So the goal of the game is to make every vertex happy. And you play according to the following rules. Perhaps you can have like a random configuration in the graph, but we are going to start just the game, but for instance, placing one coin in one vertex. And then you try, when you give money to someone, then other people is unhappy. It's the same here. So there are gonna be some vertices, when you give coins, there are gonna be some vertices that are gonna be unhappy. So to the unhappy vertices, you have to give them like enough coins so they are happy. And you give coins following this rule, okay? So the goal again is like you have this dynamic. You have this dynamic and then you wanna make everyone happy. So you start giving a coin to a vertex, let's say this vertex, but what happened is that the neighbors are unhappy. So, okay, I want to make this one happy, so I give this one coin, but then this one is unhappy and then this one is unhappy, so you have to make both happy at some point. So you give this one coin to make it happy, and this one is still unhappy, so you give that one coin, and then everyone is happy. And of course, the number of coins that you give is according to this rule that I wrote here. So there are a few things about this game. In this game, we are always replacing one positive root by another of greatest height. All the possible configurations of the game corresponds to all the positive roots. So this is how you can get all the positive roots algorithmically. So in this previous situation, for this Dinkin diagram, this would be like if you number the vertices with the simple roots, this would be, for instance, alpha 1 plus alpha 2 plus alpha 3. This would be alpha 3 plus alpha 4. And the good thing is that when you play the constant game on Dinkin diagrams, the game always ends. And in the simply laced case, it always ends in a unique terminating configuration, and this unique terminating configuration corresponds to the highest positive root. So this is why I guess it's also called the highest root game. There are a few things to mention about this game. For instance, if you play the game on this graph, this triangle, the game does not end. So the game does not always end. It just ends when the graph is a Dinkin diagram. So Daniele, now he's moving his hands. He was saying something about like one of his favorite theorems in mathematics was the classification of the completely groups by Dinkin diagrams. So this is one combinatorial way to classify them. So you can have like you can play the game on any arbitrary graph, and then you show that the only graphs where the game ends are Dinkin diagrams. So you study the combinatorics of this very same game, and then you find this sort of result. And there are analogous results for the non-simply laced case. For the non-simply laced case, it's a little bit more complicated because the graph of the configurations has two components. It has two connected components, but the game always ends. And yeah. So this is good news for us. This was really good news for us because this is more or less what we were looking for. We were looking, okay, like we need to find these strings of coroots, but we also need to, so yes, this was good because we have like an algorithmical way to find them. But however, I don't know if you remember, the roots that we are looking, they must have like a very particular shape. They must be of this form. So that means that when you play the constant game, you have to play the game somehow by giving just one token to one particular vertex and try to play the game, and somehow when you play the game and you have like this vertex only with one coin, is somehow complaints, you know, because you start to play the game and then you want to make everyone happy, but somehow you are finding these sequences of corroots, and this one it has just one coin. So at the end, the guy is not that happy with having just one coin. So because we are looking for very particular forms of corroots, and we struggle a little bit like to make this very single vertex happy. So we created like another game. And we call this game the modified constant game. So how is this game defined? So let's suppose that you have like a Dinkin diagram. You can modify the game at any vertex. So you pick up any vertex, let's say this one, and you add another vertex and one edge between these two vertices. So now, for this modified graph, you are going to play like a new constant game. So you give to this guy one token from the beginning. And then you play with the same rules as before, but with a new rule in which this vertex is always happy. Remember that we were trying to look for sequence of corroots that looks like this? So, okay, why we don't create a game in which we have that the guy is always happy from the beginning? And then you play the game with the same rules, and this one is always happy. So we call this game this new game, the modified constant game at the vertex J. So, and we show the following result. This game always ends. This is not like entirely trivial. Tell me.
Any reason you only attach one extra vertex, so one as opposed to one that each of the old vertices?
I think that when we were trying to make playing the game, at some point it was, okay, maybe just we try to do it for every vertex and then see what happens. So somehow we wanted like to study these sequences of corroots, and whenever we were trying to play with this the game there, it was like, okay, why we don't try to play it in general to see what happens? Let's try to modify the graph at every vertex, and then let's try to create this game and see what happens. So yes, so there is something that happens here that is, maybe I didn't mention, but this is not necessarily the Dinkin diagram of a company group, right? So, but it does not matter. Yes, so you have the graph, you modify the graph, you add like a new vertex, you have as many new games as vertices, and you always give to this token, to this vertex one token, and you play with the same rules, but you wanna now make everyone happy, and that one is happy from the beginning. This game ends in a unique terminating configuration. So this does not necessarily have to be that obvious, right? Because, for instance, for the classical constant game, it does not always end, for instance, for the triangle. So when we play the game, it was not entirely obvious that it will end, but we show that the game ends. Dinkin diagram. Yeah. I mean, I don't know the general case. So we also get the following result. This result is relevant if we want to show that the strings that we get by playing the game are maximal. So if you call by hj plus 1, the height of the unique terminating configuration of this game. Then the sum of the positive roots admits this decomposition as a linear combination of the simple roots. I don't know if this is known, but somehow this is something that we found when we played the game. So here are some examples. So here you have the linking diagram A4. So at this vertex, you place this new vertex and this new edge, and you are going to make, since the beginning, this vertex happy. And then you play with the same rules. So this vertex is unhappy, then you give one vertex, one token. Then this one is going to be unhappy, you give one token. This one is going to be unhappy, so then you give one token. This one is going to be unhappy, so then you give one token. You can modify another vertex. You can also modify this vertex. And then you add like this edge and this new vertex, and you give one coin. And then you just place tokens according to the rules of the constant game, but always with this vertex being happy. So this one is unhappy, so you give one coin. So this one is unhappy. This one is also unhappy. So, I mean, you are going to have like the sequence, the configurations of the game. And then you end the game when everyone is happy. To play the game at this vertex or to play the game at this vertex is the same because of symmetry for the first and the second. So at the end, what you get is the following. For the linking diagram A4, if you want to write the sum of the positive roots as a linear combination of the simple roots, the game will tell you how to do it. It's going to be 4 times alpha 1, so the sum of the last configuration, the height of the last configuration in this game, 4. For this one, for the second root, would be 6, because that is the height of this configuration, and by symmetry, there should be also here 6, and there should be also here 4. So let me explain now a little bit the idea of the proof. So these graphs, they correspond also to a Bruhat graph. So this, for this game, okay, so let me say something before. When you play the classical constant game, what happens is that in the sequence of the configurations, what you get are sequences of positive roots. But here in this game, what you get is not quite the same. It's something a little bit different. Every sequence of this game corresponds to reduced expressions of minimal length representatives of the quotient of the corresponding Weyl group with some parabolic. So yeah, so when I was making the calculations, I found, okay, these graphs look kind of very familiar to me. And yeah, these are like, every one of these sequences are going to encode like a reduced expression of a minimal length representative of a quotient of with a parabolic. And this is how you show that this game ends. Because these quotients of parabolics, they always have like a longest representative. When you play the game, the sequence of the reduced expression that it encodes, it is also encoding the number of chips that you are placing at every vertex. And at the end, this is why you get this equality. So somehow you keep track of how you play the game and the tokens that you place at every vertex. At the end of the day, you are recovering the number of tokens that you put at the end in the final configuration, and then you get the equality that I just showed you in the last slide. Okay, so this is going to imply the Mukai conjecture for the coadjoint orbits. Remember that was the original goal. The original goal was to do that sort of thing. So you have like a Dinkin diagram. Let's say this Dinkin diagram, and then you have like a SP corresponds to this set of roots. And then S minus SP will correspond to this beta. And then you start to play the game. So you start to play the game, you play here the modified version. And then you start to get like well, in this case it's simply lay, so the roots coincide with the co-roots. And then you start to play the game, and then you get beta, beta plus alpha 2, and so on, until you reach the final configuration. So this is how we get the sequences of co-roots. Sometimes it happens that the SP may have several connected components. When the SP has several connected components, you just care when beta is adjacent to one of the connected components. When it's not adjacent, is the easiest case. But when it's adjacent, you play the constant gain of the correspondence connected components. When there are several connected components adjacent to beta, so you glue the strings of co-roots, and then you manage to prove the statement. Okay, I think that I finished too early, but I think it's okay. So thank you so much for your attention, and